Sujoy, he is my postdoc, and Sabita is a graduate student, and so I'm presenting their work on their behalf. So in this work, what we did was we put together a magneto-electric composite which could be potentially useful for magnetic field sensors that could be utilized for biomedical imaging such as magnetocardiography. So I'll talk about the motivation, sample preparation results, and finally a very brief summary. Now for those who are not familiar with multiferrite composites, these contain two different phases. One is ferromagnetic, the other is ferroelectric. So the nice thing about this is, like in traditional materials, you need an electric field to control the electrical properties of a piezoelectric. Similarly, you need a magnetic field to control the properties of the magnetic phase. But when you put together a composite structure, what happens is there's coupling between the two phases through mechanical deformation. So with one particular field, you could control both electric and magnetic properties. So this can be utilized for magnetic field sensors, either DC or AC. The way it works is we have a bilayer of ferromagnet and a ferroelectric, and when I apply a magnetic field, there is magnetostriction in the ferromagnetic phase, which will be transferred to the ferroelectric phase, leading to a voltage response. And one could also argue that if I apply an electric field, you could have piezoelectric strain transferred to the ferromagnetic phase, which would manifest as a change in the magnetization or anisotropy field. So the response of the composite to a magnetic field is called direct magnetoelectric effect. That's the one we are interested in. So it could potentially be useful for detection of both AC and DC magnetic field. The way it works for magnetic field sensors of AC field, you need a bias field provided by either an electromagnet or a permanent magnet. Then you superimpose the AC that you would like to detect. And what happens is, there is magnetostriction versus bias field. You superimpose the AC field. There is AC magnetostriction leading to the voltage response. This is what we measure in the experiment. As you see here, for very low bias field, there is very little magnetostriction. So it starts out with a 0 and then it peaks when the slope is maximum. So this response essentially tracks the slope of the magnetostriction versus DC field. So the idea is to detect an AC magnetic field, but we also need a bias field to make sure that we have enough sensitivity. So that would be a hint, it would lead to a lot of problems where a magnetic field sensor that has to be utilized for biomagnetic imaging, because each sensor element will have its own magnet and leading to significant noise, so the system will lose all its sensitivity. Instead, the idea is to provide a self-biasing field for the ferromagnetic phase. That's what we did. We were able to make a ferromagnetic phase which has self-bias and also very high sensitivity because of strong magnetostriction in the piezomagnetic coefficient. So our approach was to make a composite for the ferromagnetic phase with two different oxides. One is the spinel ferrite, which has high magnetostriction. The other is M-type hexagonal ferrite with very high uniaxial magnetocrystalline anisotropy. So we chose nickel ferrite and nickel zinc for the spinel ferrite, and M-type strontium or barium ferrite for the hexagonal ferrites. And the way we put together the composite was to make these two phases separately, nickel ferrite and nickel zinc, and the M-type ferrites, by traditional ceramic processing, then barium ferrite has very high index anisotropy on the order of 17 kilogauss. Strontium ferrite has about 18 kilogauss. So we made composites with a series of weight percent of the hexaferrite and the spinel ferrite. For example, this particular composition, we call it BNX. X represents the weight percentage for the nickel ferrite. In a similar way, NZ is nickel zinc. X is once again the weight percent of the spinel ferrite. And as I just mentioned, we made these by ceramic processing, and after that, the powders are mixed in proper proportion and sintered at 1250. And these are the X-ray diffraction data for the composites. As you see here, we don't see any impurity phases except at very high nickel ferrite or nickel zinc composition. This is the impurity phase which we identified as an antiferromagnetic in nature. So it will not affect the ferromagnetic phase in true sense. So these are the scanning electron microscope images for the composites. As you see here, these are the SEM images with increasing amount of nickel ferrite. And you see here the crystallites belonging to the hexagonal ferrite, and also at higher nickel ferrite composition. But at very low nickel ferrite, there is hardly any hexaferrite crystallites, which is rather puzzling. There should be more of that. So these are the magnetostriction for the spinel hexaferrite composites, and it's pretty good. I think the maximum value is around minus 25 parts per million. It doesn't quite saturate for fields up to 3 kilogauss. That's because there is very large fraction of hexagonal ferrite. And we are able to find the anisotropy field for the composite. These measurements were done in ferromagnetic resonance. Measurements were done on platelets of these composite structures. And what is shown here is the anisotropy field we determined from FMR and static magnetization measurements. Negative sign represents anisotropy perpendicular to the plane, and the positive sign is in plane anisotropy. So the way it looks like, all the hexagonal ferrite, these platelets, they have C-axis in plane. That's the reason for a very large in-plane anisotropy field. It's pretty good. It's as high as 7 kiloarsted for some of these composites. So then what we did was to make a bilayer of these ferromagnetic platelets with PZT, and they were bonded by several different techniques, including epoxy bonding and eutectic bonding, and they were subjected to DC magnetic field and then superimposed on it an AC field. And the voltage response was measured for two different field orientations. One is all the magnetic fields, both AC and DC, are in plane, and the PZT was poled perpendicular to the plane. The voltage was measured across the PZT. PZT has already, the one that we got was from vendors with silver electrodes on them and pre-poled. So all we need to do is just make a composite. So then the other was what we call longitudinal. In this case, both AC and DC magnetic fields are perpendicular to the plane, but also the PZT was poled out of plane. These are some of the data. This is the voltage response versus bias field. As you see here, at zero bias, there is significant voltage response. So it is the effect of self-biasing for the ferromagnetic phase. And these are data for increasing amount of nickel ferrite. So with increasing nickel ferrite, the overall voltage response increases. And this also has zero field response. And these are even higher nickel ferrite composition. 75, 8%, and 95. So what we plotted here is the overall voltage response at zero field as well as the peak values. And both of them show maximum at around 80% of nickel ferrite. And these are the similar data for all the fields perpendicular to the plane. And once again, you see the zero bias voltage response for all these compositions. And as I mentioned earlier, we also made similar composites with strontium hexaferrite and nickel ferrite, and they were made into bilayers with PZT. And these are similar data. It essentially is similar to what we got with barium hexaferrite. The only thing is the overall voltage response for this composite is somewhat weaker than the previous series. And these are zero bias voltage response as well as the peak response for this series of samples. So to conclude, we are able to make essentially defect-free composites of hexaferrite and nickel ferrite. And these have very high magnetostriction as well as a built-in bias magnetic field that could be utilized to put together magnetoelectric magnetic sensors of both AC as well as DC, potentially for imaging applications such as magnetocardiography. There's a lot more work to be done on this because the overall voltage response is rather weak. We are able to make, in the past, under a DARPA program, sensors as good as 20 picotesla at 1 hertz. So these values I showed, they are nowhere comparable to those sensors we made. They are made of med glass, aluminum nitride, or med glass, and quartz or langatite. So that's a whole different story. But here, these materials have very good promise for utilization of materials for magnetic field sensors, which are self-biased. You don't need an external magnet to bias them, and they can be made into an array for imaging applications. Thank you.